Let us now discuss how we will generate PWM for the push-pull topology. Let me draw an op-amp comparator. You have plus and minus. To the minus, I will give a triangular carrier. And to the plus, I will give the control signal or the control voltage like that, which is supposed to modulate the triangular carrier. So let us draw the waveform with respect to t. I have this triangular carrier in this fashion, 0 to some positive value, and the modulation signal Vc is shown here in green. Let us see what is the output like. So let us mark the intersection points and bring it down in time and project it onto the time scale. So whenever Vc is greater than triangle, because triangle we given to the minus and Vc control voltage to the plus, whenever the control voltage is higher than the triangle, the output will be positive, otherwise 0. Positive, 0, it goes like that. Depends upon what type of op-amp you are using. If you are using a bipolar amp, then a bipolar op-amp, then it will go positive, minus, like that. So let us say that we are having a unipolar op-amp with only VCC, VSS grounded. Therefore, you will see output going positive to 0 in this fashion, just thereby giving a pulse width modulated waveform. So if you call this one as VA, this would be VA. There are many integrated circuit, PWM integrated circuits that use, instead of a triangular carrier, they use a sawtooth carrier. Much easier to generate. So they use that one. This is also fine. You can superimpose VC, that is the control signal, like this, and then mark off the intersection points in this fashion. This whenever the sawtooth happens, that is whenever the reset happens, that would be the start of the period. So we can say period Ts is of that duration here. And whenever the Vc control signal is greater than the triangle or the sawtooth, you have a high, then a low, high, low, so on. And you get a pulse width modulated waveform in this fashion. So this is typically used in many PWM ICs, sawtooth, because sawtooth generation is much easier. Now, let me add one more op-amp, one more comparator. And to that comparator minus, I am giving the triangular carrier or sawtooth carrier, and to the plus I am giving another signal, fixed DC. I am calling that as VD, and it's a fixed DC. Let us see what this does, and then the output of these two, I will erase that. I will put two diodes here and OR them. So I am going to OR the outputs of these two. One is having a control signal Vc, another is having a fixed DC signal Vd. So let us superimpose on this triangular carrier and see what happens. So you see that, and here also this we call as Vd, this is Vd. So you see that here there is a minimum pulse width. So whenever the Vc signal, control signal, is higher than Vd, there is no issue, the operation is normal. When Vd becomes lesser than Vc, then what dominates is Vd, and Vd will dictate and it will issue a minimum pulse width command. So you will be assured of a minimum pulse width, and even in the sawtooth case, minimum pulse width is assured. In the case of sawtooth case, you see that always it is starting from one end. So one end is determined because of this vertical drop, reset. One end is determined, so modulation is always on the other end. In the case of the triangle, modulation happens on both ends. So in both the cases, you have a minimum pulse width which will come into the picture. So this will declare minimum duty cycle limit for the circuit. So this way you can achieve minimum duty cycle. Even for single-ended operations like the forward converter and the non-isolated converters, you can use this method. Let us now assume for now that we have a pulse width modulated waveform VA, a single pulse width modulated waveform, and using that single pulse width modulated waveform, let us develop the mutually exclusive drives that we can obtain or we should obtain for Q1 and Q2. Q1 and Q2 should have mutually exclusive on times. And how do we get that? It is not exactly a 180-degree phase shifted waveform. You should understand that Q1 is on for some time, Q2 is on for some time, and then in between there are times when Q1 and Q2 are both off. So we have to obtain a wave shape which will do that. So let us continue the circuit diagram further. Now from VA, let it trigger clock of a D flip-flop. You have Q and Q bar, and the output of Q bar, let us connect it to the D input. So what do we have? We have a toggle flip-flop. So the output of the toggle flip-flop, let me steer it through AND gates, and the second inputs of the AND gates, I will give it to one output steering control steering control pin. This has an important effect on the final output of the PWM. I will discuss this. Just for now, assume that this is either 1 or 0, a pin which can take value 1 or 0. Now the output of the AND gates are given to NOR gates like this, and the output of the NOR gates are given to the BJT or a transistor, which can be further amplified and then driving the power switches. So these two NOR gates will have the second input coming from VA in this fashion. So this will be the steering logic that we will be using for the PWM. Let me push this a bit up. So now let me mark this as A, and this as B, and this as AA, and this as BB, so that we can distinguish the waveforms. Now let me say that VA, we have VA, which is a PWM modulated waveform. Now let me divide the time into segments, each of TS width. So within the TS, you are having a portion of the waveform, a pulse width modulated waveform, which appears like this, which we just developed for VA. So you have the pulse width pulse width modulated waveform coming like this. Now this is given to the clock of the D flip-flop. So let us say that the D flip-flop will be edge triggered on the rising edge, and so on the rising edge, let the toggling action happen. So Q will go high on every rising edge. The Q will toggle on every rising edge. So let us say it starts from 0, it goes high here, and on this rising edge, Q will go low, and then again on this rising edge goes high, here again low, high, low, like that. So this is toggle flip-flop toggling. Q bar is opposite of 180 degrees phase opposite of Q. So it starts with the low, then toggles high, low, like that. So this way you get the Q bar output also. Now you see these AND gates. If the output steering control is 1, then A is same as Q, B is same as Q bar. So let us say that these are A and B waveforms if output steering control is equal to 1, meaning that the AND gates are enabled. So this will pass through, have A and B coming to one of the inputs of the NOR gates. So what is AA and BB? We'll see that. So AA and BB. Now this is waveform A and this is waveform VA. This is NOR gate. So it will be A plus VA whole bar, which is A bar and VA bar, isn't it? So this is A bar waveform. So let me look at only those portions where you will get a pulse. So I am just marking these portions. So you see this is A bar, this will be high, and during that time VA bar, this portion will be high. So what I'm showing here in the cursor. Likewise this portion. So I'm marking those portions and I'm drawing the AA waveform. So it will be high only on this places. Now BB, let me mark, it is now B bar into B bar and VA bar. So you will see these are the portions where BB will go high, and I will write it down like that. So you see here, AA and BB waveforms are mutually exclusive. You can give Q1 on here, Q2 on, Q1 on, Q2 on, Q1 on, so on. And these are pulse width modulated because they are coming from the primary pulse width modulated waveform VA. So in this way, you can generate two mutually exclusive DTS period waveforms which can be given to two different switches Q1 and Q2 and where they are never on simultaneously. They are mutually exclusively on. So this is the kind of pulse steering that we do and give it to the switches Q1 and Q2 of the push-pull circuit. Here again you will see that there is no correction for flux walking. Typically many of the PWM ICs do not provide correction for flux walking. You have to do that externally. However, you do also find PWM ICs which give flux walking correction. Another point you have to note is what happens when the output steering control pin is 0. When output steering control pin is 0, A and B are 0, this latch and this points are out of action. So VA comes directly to the NOR gates of these two. AA and BB both will be same except inverted, and you will have a pulse width modulated waveform, both same. AA and BB both same simultaneously. So you can use that one to drive a single switch or two switches with enhanced drive capability. A typical PWM IC of the structure that we just now described is a TL494 pulse width modulation IC. Very simple, around 10 rupees in cost. And the block diagram, internal block diagram, it's a Texas Instruments IC. Internal block diagram is similar to the one that we discussed. It has a simple block diagram. This is a 16-pin IC and easily available in the market. Download its data sheet, and you can see there is a test circuit here, and you can set the carrier frequency by setting the RT-CT waveform. And if you monitor the voltage waveform at pin 5 across CT, you will see that it is a sawtooth carrier. So this is based on a sawtooth carrier, and then you have two output waveforms, C1 and C2 collectors, the internal transistors, collector 1, emitter 1, collector 2, emitter 1, which you can externally connect and take out the PWM outputs. The functional block diagram similar to the one that we discussed. You see an internal oscillator RT-CT generating the sawtooth. There is a dead time controller comparator. There are two other comparators, error amplifier 1 and 2. They are internally ORed. And there is a PWM that is given to the clock. There is a D flip-flop with toggle flip-flop mode operation. Then you have the steering control logic and two AND gates, and then the NOR gates given to the internal transistors. There is an internal reference voltage which you can use. So you see the logic is very similar. When you give the output steering control 1, then you will see that you will get mutually exclusive outputs which you can use for push-pull circuits or even half-bridge circuits and full-bridge circuits. When you make the output control pin 0, then the PWM directly comes to both, and both are identical PWM outputs. You can use the two internal BJTs to enhance the drive signal. So this is an interesting and easily available popular PWM IC available in the market.